right, so we are going to start, not finish, talking about comparing two means, okay, which is different than what we've been doing. What did we do prior? We compared to what? Proportions, right? And the example that we just did talked about comparing the proportions of people that quit smoking in different treatment groups. So we're going to talk about comparing two means. Now, we've had experience with looking at two different means back in our last unit. And what was that called? Matched pairs. Very good. So we've had a matched pairs, and remember last class we looked at the difference between looking at matched versus independent samples, right? We never match with proportions, but we can match with means, and we just end up subtracting those and end up dealing with one sample anyway, right? Well, when you have two independent samples, we're not going to match. So by the end of Friday, not today, we should be able to talk about all these different things, compute probabilities between two different independent sample means, look at conditions. We're going to do that part today, and we'll look at, there's going to be a confidence interval, there's going to be a hypothesis test, significance test, same thing, etc. So let's kind of jump into the notation. And if you remember last class, we talked about this same parameter versus statistic notation with proportions. But now we're going to talk about means. And so we know, just again, the subscript simply means from sample 1 versus sample 2. And we're going to write our hypotheses when we get there in terms of the parameter always. Do you agree? So we should have mu1, mu2. By the way, it is a U with a long tail on the left. I'm looking at a lot of you writing it, and they look like W's. So just be careful, okay? So they are U's with a long tail on the left. It's called mu. It's the Greek letter. So mu1, mu2 on our statistic, which is our sample that we're collecting, is in terms of X bar, and it's just the same subscript notation, okay? So just like what we did last class, we can state some things that the shape is going to be normal. This time, though, the normal condition when we talk about means is not NP is greater than 10. We're looking at what? If the sample size is greater than 30, rarely it is, so what do we need to check for? The graphs, okay? And we'll have to look at 4 different graphs this time because we have to look for 2 for sample 1 and 2 for sample 2, right? So you'll have to check the graphs for the both independent samples, much like Kiana drew both of the conditions for both samples with proportions. We're going to do both samples again for means, okay? What is the test statistic for means? Listen to my question again. So the test statistic for proportions was Z. Do you agree? It was a Z value. What is it for means? T. If we don't know the population standard deviation. We rarely, if ever, know that. If we did know it, we would still use these. But we rarely do. So that's when we use our test statistic, our student's T. There's so many names for this darn thing. Pearson's T. I forget what else it's called. The T, okay? What do we have to be careful of when we use T's? Begins with a degree. Degree of freedom. And what was it in a 1 sample? Sample size minus 1. Good. What do you think is going to happen when you have 2 samples? That's a good guess, but that's not true, actually. Well, there's 2 different answers to my question, okay? There is a really complicated formula. It's in my old book. It's probably in this one, too. That shows you the calculation for the degree of freedom. I will never ask you to do that calculation because it's like redonkadonk, okay? The calculator uses that formula and gives you a degree of freedom on the calculator. And it is the most accurate degree of freedom you can use. Perfectly okay for you just to tell me df equals and then whatever the calculator gives you. Fair enough? There is something called the best estimate, which is the smaller of the 2 n minus 1s. So sample size 1 minus 1, sample size 2 minus 1, and then whichever one is smaller, that's the degree of freedom you use. Okay? That's a general estimate. Both are accepted by AP, both are fine, both are okay, don't care. All right? But you just have to be mindful of degree of freedom, that's all. Okay, cool. We kind of looked at this last time as well. When you have a normal sample for sample 1, a normal sample for sample 2, the difference also becomes normal. We talked about that with proportions. It holds true for means as well, which means that's why we can check them independently, and then the subtraction of them will also equal normal. Okay? I'd like to just jump in to an example. So let's do an actual real example. This one. So here we have it. A little hard to read probably. Is it small? Yeah, big enough. Okay. So it says the Wade Tract Preserve in Georgia is an old growth forest of longleaf pines that has survived in a relatively undisturbed state for hundreds of years. One question of interest to foresters who study the area is how do the size of longleaf pine trees in the northern and southern halves of the forest compare? To find out, researchers took random samples of 30 trees, that sample size is interesting, from each half and measured the diameter at breast height in centimeters. Comparative box plots of the data and summary statistics are shown. By the way, this is called computer output. This is just a Minitab output. Minitab is old, right? It's an old piece of software. Fathom is a little bit more. We're going to be looking at computer outputs and what you're going to look at for the next few weeks at least. Anyway, it says construct and interpret a confidence interval, a 90% confidence interval, for the difference in the mean for the longleaf pines in the northern and southern halves of this preserve. Okay, so we're actually given some key pieces of information here. So let's think about what we should do first. Check our conditions. Perfect. So what kind of conditions do we need to check for? There are 3 that we check twice, right? So let's start. The random one, okay? So does it say anything about how the samples were collected? It does. It does say, in fact, that the samples were collected random samples from each. Do you agree? That's important. So with sample 1, they were collected randomly, the northern half were collected randomly, and the southern half were collected randomly. What's the second condition you want to check? Independence, which would then translate, I'm going to need you to get off your phone for me, okay? Thank you, Elvis. All right, so the independent example is at 10%. So what are we looking at? What number is less than 10%? 30. Good. Okay. So 30 is less than 10% from each half. Okay. Not from each half. 30 is less than 10% of all the trees in the northern, and 30 is also less than 10% of all the trees in the southern. We have to assume that. We have to assume it's a large enough preserve with trees. Okay? Does it say how many? It doesn't say how many there are, but we're just going to assume that. What's the last condition? The normal condition, and so with means, we're looking for sample size greater than 30 or equal to 30. Do we have that? Yes. So we don't even need to worry about the box plots, do we? But they gave them to us. There aren't any outliers. They're not super duper symmetric, but do we care? Because our sample size is big enough, right? So we're fine. Good. All right. Okay, so we've checked our conditions. Give me the second thing based on, before I want to show you some other things, and not yet. Looking at the problem, if we're trying to construct a confidence interval for the difference in the mean, what other piece of information on the screen that you see do we need to use? What's our, I'm going to leave that, that's my question. What other information do you see? The means. What am I going to do with those 2 means? Subtract them. Okay? Do you agree? That's important information, isn't it? In other words, this is like x bar 1 and x bar 2. Does that make sense? Those are our sample statistics. Important information. Okay? Good. What is our parameter of interest? In our state, or actually we're in the plan part, right? We had check our conditions and then we're going to go on. So what are we trying to, it says down here, I'll just go ahead and scroll down. Okay? So our parameter of interest is the true mean, right, of dBH, something, I don't, diameter breast height, I'm not sure, okay, of all trees in the southern half of the forest, and U2 would be the true mean in all of the northern half. It is very important here that you tell me which one is northern and which one is southern, because it's not talking about group 1, group 2. Those numbers are not in the problem. Do you agree? So you need to be clear about which one is in sample 1 and which one is in sample 2. The way that they wrote it, they did southern half as, oh, you're right, thank you. So let me do that now. The way that they wrote it, this would be true, correct? Good, that's fine. And we're going to be talking about, we're trying to capture that difference. All right. So what do you think we're going to do? Well, we need formulas to approximate standard error, and we need to think about what our T is. Do you agree? Our T star. Because our formula is, in fact, this. So here's our problem. We've already talked about do. All right, this is really small, y'all. I'm so sorry. Let's do this. I'm trying to make it bigger. Don't look, don't look. It's a surprise. Haha, just kidding. All right, that's really small. I'm sorry, it's so small. But I can just tell you what it says. Maybe. All right, so here we're looking at constructing a confidence interval. We're looking at the mu1 minus u2. It says we'll use the conservative degree of freedom of 29. Why is that the conservative? What did I just say about degree of freedom? So they're both 30. Do you agree? So 30 minus 1 is 29. So we're just going to use 29. Your calculator, if you did this, if you did it on the calculator, would give you a different number. That's the more accurate one. Doesn't matter though. Okay? It has to do with the formula that they use. Okay? All right. Here is the formula. Let's see if it makes sense. Does x1 minus x bar 1 minus x bar 2 make sense for the beginning? Isn't it parameter? I'm a liar. Statistic plus or minus critical value times the standard deviation? Okay? So my question becomes, where'd these numbers come from? 14.26 and 17.5. Well, hopefully they gave that in the computer printout. It does not say that they did. So that would be something, oh, maybe, hang on. It was hidden. All right, we needed that information, right? So that is information that had to be in our computer printout. We can't just make those numbers up, okay? So we had to have our sample standard deviation from sample 2 and our sample standard deviation from sample 1. So that's important information. All right? Also, where those numbers came from. Do you agree? Okay. Where did 1.699 come from? So are we okay with this is like x bar 1, and this is x bar 2, and this is right here is sample size, I'm sorry, sample standard deviation 1 and sample standard deviation 2, right? And then our sample sizes were both 30. Notice our formula here. That's new. So make sure that you have that. I think it's on our formula sheet as well. If you look at difference of means on your formula sheet, it's still in the last column, but kind of midway down. So the formula is there. You don't have to memorize it. But again, my question becomes, where did the 1.699 come from? Inverse T. Very good. So if we think about T star, it is in fact inverse T, but what numbers go in there? Because it's a 90% confidence interval, the middle is 90%, each tail is 5%, So we're going to do inverse t of 95%. Are we okay with that? And then what degree of freedom did we suggest, or did we say we were going to use? So plug that into your calculator for me. Just double check that I was right, that it is 1.699. I'm just going to look over your shoulder. Did you get 1.699? Okay. Good. So that should be 1.699. So I am okay at this point is if you show me where all the numbers come from, we now can just go ahead and give me an interval, right? And I'm okay if you plug it into your calculator. What is that? So let's try this on our calculator. And let's see if we get the same numbers. So I'm going to turn the lights down just so we can see it. And what are we going to, what test, what are we looking for here? It's not a test. So it's a two sample t interval. Would you agree with that? All right, we don't want the data. Do you agree? We don't have it in lists or anything. We want it in stats. All right, so I don't have the number. Oh, they're right here. What's x bar 1? 34.5. And S1 was 14.26. Sample size 1 is 30. Huh? Nope, just the regular. It'll square it for you. Okay. That's just part of the formula. The mean of the second sample was 23.7. The sample standard deviation for sample 2 was 17.5. And we again have a sample size of 30. Oh, our confidence level was 90. Yeah? What's nice is that if you're doing the right test, the calculator asks you for the right information. So if you're doing the test on the calculator and you don't have a piece of the information, you're doing the wrong thing. Okay? So that's kind of nice for us to just double check. Do we pool? Never. I shouldn't say never. There's only a rare instance where you pool, and I'm not even going to talk to you about when it is, because when do we pool? Right. Hypothesis test for two proportions, right? Okay. So we're going to go ahead and calculate. And hopefully 3.9 to 17, that's a big interval, isn't it? All right. Huh. What do you notice about that interval right away? When you have two samples, what are you looking for it to capture? 0, does it? So that tells us something, doesn't it? What does it tell us? That one part of the forest has bigger trees by at least a mean of 3.9 to 17.7. Would you agree? Which one is it? Depends on how we named it, which is why it's so important that we talk about which one is which, and when we state our parameter, we're clear as to which one is northern versus which one is southern. Okay? So it'll help us interpret our confidence interval as well. Hopefully we got the same thing. Yeah? I hope. And I hate that we did this in red, but it says we are 90% confident that the interval from 3.83 to 17.83 centimeters captures the difference in the actual mean DBH of the southern trees and the actual mean of the DBH of the northern trees. The interval does suggest that the mean diameter of the southern trees is larger by that much, or by between that much. Yeah? How do we feel? Not a whole lot different. It's just that we have some new formulas to worry about. And the formulas that we have to worry about are all with standard deviation. Right? They're the new ones. Justin. Right. The degree of freedom on the calculator will be different, right? Which means that your T star is going to be different on the calculator, which means that this interval will be a little bit different than what the calculator says. Does that make sense? And that's okay. It has all because of degree of freedom. Okay? That's the only difference. It should be close. Is it close? Okay. Close is good. process is important. Yes? It will tell you. Okay, so if I went, so it doesn't say it with the interval, does it? Okay, but if I go here and go to tests and do a 2-sample t-test, again with the same information, notice it stores it between the interval and the test. Have you guys noticed that when we flip back and forth, that it stores it for you? If I go ahead here, and again, don't pull, oops, except for, I'm looking that, it would be greater than, right? Calculate, and we get a degree of freedom of 55.7. Oh, does the interval tell you too? Oh, I'm sorry, I didn't realize that. Okay, so in the interval, it also tells you that. I'm so sorry, I didn't realize. So let me look again. So 2-sample t interval. Let's just do it at the output again. Oh, it does. Look at that. Perfect. So it's because, remember I told you the calculator uses this complex formula to find degree of freedom when you have 2 independent samples, and I'll never ask you to use that. So we did an estimate degree of freedom of 29. Theirs is a little bit more precise. The higher degree of freedom, the better, the more accurate, but we just have to look at our sample individually. It's because of the degree of freedom, okay? So your degree of freedom, if you used a degree of freedom of 55.7, like if I change this number to 55.7, it'd be the same. Try it. Prove me wrong. I hope I'm not, but I'm pretty sure I am. Right, not wrong. All right, so that's all I wanted to do today was confidence intervals. We'll pick up proportions, we'll pick up the interval, I can't even speak. We will pick up the hypothesis test for 2-sample means on Friday after your quiz. Are you looking at your quiz? Your quiz is on Friday, is on 10.1. It's on the proportions, just proportions, 2-sample proportions, which is why we practiced again this morning, okay? So you have the back of that. How about if I post the answer key on our webpage? That way you have it before you come in for the quiz on Friday. Is that reasonable? Okay, I'll do that for sure.